all of you have tried that particular question, homework problem that I have given to you. Anyone has tried that? Tell me this. Yeah, very good morning to all of you. Okay, guys. So let's start the session. Yes. So we are discussing about the fluid statics, and we have just started our discussion onto that, and we have seen that somewhat the differences between the pressure and the stress, that at a particular point the pressure value will be same in all the directions, right? As it is not having any specific directions, so we say that it is a scalar quantity. Rather to say about the pressure, we also talked about something about the stress, that stress is a second order tensor, right? That means we for denoting the stress value, we not only require the particularly what we say. See, so whenever we are representing the stress, so we require two indices, right? What is it? X and X. What is the meaning of that thing? One will be required. Not only you will be required that particular plane, but you need to specify the directions of that stress which is acting, right? That means if I draw the cubical element, so in that cubical element, if I just make it something like this will be, for example, x-axis, y and z. So what about this sigma? On which phase it is acting? This is acting on a particular x phase, right? What is the meaning of phase? The phase which is perpendicular to what? Particular plane, right? Now, I am saying that this particular plane is a x plane, right? Because x axis is passing through that, right? that is the x phase and x direction, right? So this one will denote it the phase or a plane on which it is acting and directions, right? Something like this. So if I represent it like this, then what we can write on a y phase in x direction. So this will be yx, right? So we used to represent it by two indices, right? That is a second order tensor, right? Second order tensor. That is a, but you, whenever you observe the fluid element, whenever you observe any fluid element, same cubical element, if I just draw it, so what I will just say, whatever the pressure will be acting, the pressure will be denoted by like this. We don't say at all that it is px, it is py, it is pz, because px equal to py equal to pz, that is equal to minus p. So no need to specify the direction for the case of pressure, right? That is the we have the differences between the pressure and the stress, right? And this particularly hydrostatic, this is what we are calling. This is we are calling hydrostatic state of stress, right? This is a general state of stress condition. General. We will talk in the strength of material. As of now, we are dealing with the some basic understanding. General state of stress. Of course, you will be having some another. I only saw on. I just shown you this two component of the stresses, but actually there is a matrix. There will be totally nine component. In that, three components will be what same, and six components are independent, and three components are equal. Actually, tau xy is equal to tau yx, tau xz is equal to tau zx, and tau what we say zy equal to tau yz. Right. Total components of the stress are nine at a particular point. So these are the some differences what we have observed in case of pressure and the stress. So that is also one of the famous question that can be asked about the differences between the pressure and stress. One more difference is there. Pressure can be measured with the help of what? Strain gauges, right? Sorry, whatever the pressure gauges are there, with the help of pressure gauges, we can able to measure the pressure, right? Yes or no, guys? Getting my point? What I'm saying? No distortion will occur. There will be only volumetric changes will happen, right? Only volumetric energy will be stored, right? Volumetric strain energy will be stored. There will not be any distortion energy in this case. Tell me, guys, how to measure the pressure? How to measure the pressure? Pressure can be measured by pressure gauges, right? Have you seen that? We just connect it like this, and we can able to measure the whatever the pressure is there of a particular control volume or particular room, right? But stress cannot be measured directly, right? Stress, for measuring the stress, of course we have the universal testing machine, but universal testing machine will not give directly the values of that. It will give the readings of different deformations, and through making the table we can able to get the values of sigma. What is that? Force divided by area, right? So force that will be applied by the universal testing machine directly. There is no such an instrument called stress gauge or something like that, by means of which we can measure the stress. No, we don't have such an instrument directly. We have to perform the experiment, right? Now, so magnitude of the pressure value at a particular point will be same in all the directions. That is valid when the fluid is under rest condition, but that is also valid when the fluid is under what? In a rigid body motions, right? Now, what is a rigid body motion? We will see that. That is a different phenomena. And one more thing I would like to tell you that here, okay, so whenever the fluid is subjected to hydrostatic state of stress, whenever the fluid is subjected to hydrostatic state of stress conditions, you will be having, just wait, yes, whenever the fluid is subjected to hydrostatic state of stress, For example, you are talking about the fluid case where it is being subjected to hydrostatic state of a stress condition like this, P, P, and P. So if I make it 2D figure of that, something like this will be P, this will be P. Now, if you just make the Mohr circle of that, and I'm talking about the hydrostatic state of a stress. Hydrostatic state of stress. Now, in case of hydrostatic state of stress conditions, if you just calculate the tau s theta, right? When you just calculate the tau s theta at an angle theta from a plane, what is the value of tau s theta if you just want to calculate, right? So this formula I have discussed, I think in the particularly demo class, what is the shear stress formula at an angle theta? We have seen this one. What is that? Sigma x minus sigma y by 2 minus of that sine 2 theta plus tau xy cos 2 theta. As this element, stress element, is not subjected to any tau xy. As you can see, there is a no such a value called tau xy. Tau xy is 0, right? This is 0. Sigma x is what? Minus p. Sigma y is what? Minus p. Once again, this will be 0. So tau s theta will become 0. That means when tau s theta will be 0, my dear friend, right? What you are calling about that? Tell me, guys. There will not be any shear stress will be acting in a fluid element which is being subjected to hydrostatic state of stress conditions. Getting my point? The fluid element will not be subjected to any kind of shear stresses whenever the fluid is under what? Subjected to hydrostatic state of stress conditions. Make a note of it. So that's why the reason you will observe that there will not be any shear deformations whenever the fluid is subjected to hydrostatic state of stress conditions. Whenever the fluid element is subjected to hydrostatic state of stress conditions, they will never gonna undergo, right? They will never undergo distortion. What is the meaning of distortion? See, I'm talking about the fluid element. Yes, they can basically what? Increase or decrease. As the pressure is acting, definitely the volume will decrease. Definitely, total volume will decrease. There is a no argument in that. Because of the pressure value, whatever I'm saying that they may decrease their volume. There will be some volumetric deformations. There will be some linear deformation in x, y, z directions, but there cannot be any shear deformations, right? That's why you observe sea rock or submarines. Whatever the submarines are there, the submarines are basically subjected to what? They are never gonna fail. Fail by distortion. They will always basically fail by normal stresses, right? Make a note of it. Correct. There will not be any shape changes, right? I'm talking about shear deformation means something like this. This is a fluid element. Now the shape will change like this, or maybe we can have the shape changes like this. Or if we have the deformation like this, something like this. These are the shape changes. This is only possible when the fluid element is subjected to some kind of shear stresses, right? This tau value. When there is a no tau, see, tau s theta is 0 means what? Not only on one particular plane, on any plane, it is independent of orientations of planes. That means Whether you rotate theta equal to 0, theta equal to 90, theta equal to 45, theta equal to 30, theta equal to what? 46 degrees, theta is equal to what? 76 degrees, theta is equal to what? 200 degree, whatever the degree you rotate it, everywhere tau s theta will be 0, right? So make a note of it. Sea rock, submarines fails by normal stresses, right? They will never undergo distortion or CA deformations. Because see, tau s theta is what? According to Hooke's law for this air, tau s is what? Directly proportional to gamma xy. For example, gamma, right? This is what? Gamma is what, my different. This is nothing but say strain, right? And in case of fluid, that will become what? Say strain rate. If tau s is 0, then this will also be 0. That is as simple as that. Is that clear, all of you? All of you are understanding or not? When we discuss the in the solid mechanics, the picture will be more clear when we talk about the different types of state of stress condition. In that, one of the special case, hydrostatic state of stress conditions. Which, see, you might be thinking, sir, this is a solid body or fluid body. See, whenever we talk about the solid body, we don't say pressure value, we say stress. We say 3D compressive stress of equal magnitude. But the moment we are talking about the fluid, liquid or gases, we don't say stress. We say that, okay, pressure value is acting, right? So that's why the name, basically in the basics only, I have given that we speak of pressure only when we deal with the gas or liquid, right? And that is not given by me, that is given by Sinjal, right? So definitely there has to be validity of that statement. So whatever the things we have discussed in the past, I would say 20 minutes, or in the last class, in the last 10 minutes, 30 minutes will play a very important role whenever you go for any interview in MTech. Also, suppose you are opting for any, interdisciplinary branches in ISC, definitely you have to face the interviews, and these are the questions will be there. Now, once it is done, let me know. Can I move to the next segment? See, guys, note down the next segment, the types of pressure we are going to see. So note down, as you can see this particular diagram. So make a note of it. Very, very important note. Actual pressure at a given position is called absolute pressure. So any law, you know that at a particular point the pressure is same in all the directions. We say something law. Tell me this. Pascal law. Now tell me whether Pascal law is only applicable for the fluid at the rest condition, or when the fluid is under certain type of situation where it is under motion also it is applicable. Because we always heard the Pascal law whenever the fluid is at the rest. That is the starting of the statement. The pressure is same in all the directions. But remember that the Pascal law is applicable even though the fluid is undergoing motion. That is a rigid body motion. Even though it has the acceleration, still we talk about the validity of the Pascal law. How and why? let's we will discuss about that in detail about discussing this particular slide. So guys, here the few points I would like to give. Actual pressure at a given location will always tells you the absolute pressure value. Second thing, you just make a note of it, note number one, and you can make here note number two as absolute pressure can never be negative. Absolute pressure can never be negative, my dear friend. So what is the first thing you're observing? This is a reference one, right? This is my zero line. Definitely you'll be having some atmospheric pressure. What is that value? 101.325 kilopascal or 1 bar, or let's say 1 atm, right? 1 atm. So here what I'm saying that you will be having certain values. If at a particular point, right, whenever you have the absolute pressure more than atm pressure, then whatever the excess pressure is there apart from this atm pressure, that we say gauge pressure, right? So what is the definition of the positive gauge pressure? No down. Positive gauge pressure, what is the definition, my different? The definition is whenever absolute pressure, when p absolute is more than p atm, then the pressure is known as positive gauge pressure. Then the pressure is known as positive gauge pressure. Or we can also write in the next slide. Okay. But sometimes what is happening, the pressure might be total pressure might be lower than atm pressure, right? When the total pressure is less than atm pressure, when the total pressure is less than p atm, total pressure means absolute pressure. In that case, my dear friend, you will be having negative gauge pressure. That negative gauge pressure will be called as vacuum pressure. That negative gauge pressure only we are calling vacuum pressure. Make a note of it, very very important. So p absolute is given as p atm plus p gauge. P absolute is also given as p atm minus p vacuum. Done, all of you? All of you have noted down? So we also sometimes we say total pressure. This is to be as total pressure. Now, for example, you will see the example here. One example, a vacuum gauge. A vacuum gauge is connected to the chamber, right? a vacuum gauge which is connected to a chamber. Let's suppose there is a chamber and I'm connecting one gauge which shows me the reading of 5.8 Pascal square inch. That is something, other than, in America, they used to follow this unit of pressure. Here we deal with the kilopascal or megapascal, something like that. A vacuum gauge connected to the chamber reads the pressure value 5.8 Pascal square inch at a particular locations, right? Where the atmospheric pressure, right? Where the atmospheric pressure, whatever the atmospheric pressure is there, PATM, that is given as 14.5 psi. They are asking what is the absolute pressure in the particular chamber. Tell me, guys. So whatever the vacuum gauge is there, remember vacuum gauge will give me negative gauge pressure. Whatever the vacuum gauge is there, directly it will give me the negative gauge pressure. What is the gauge pressure here? Minus 5.8 psi. So what is the total pressure, or what is the absolute pressure? PATM minus P gauge pressure. So what we can write? PATM is what? 14.5 minus 5.8. When you calculate, you will be getting what? 8.7 Pascal square inch. And that is so obvious that absolute pressure at a particular location, at this location, the absolute pressure, my dear friend, is less than PATM. That's why you have the what? Negative gauge pressure. That's why you have the what? Vacuum. So remember that absolute pressure cannot be negative, even though gauge pressure can be negative, but absolute pressure cannot be negative. Then all of you have noted down. Can I move to the next one? So here we will try to see the Pascal law. Note down. Pascal law. Note down this statement. According to Pascal law, pressure at a point, pressure at a point in a static fluid, pressure at a particular point in a static fluid is equal in all directions. Is equal in all the directions. That means at a particular point, the pressure might be acting here P3, pressure might be acting over here P1 and P2. So according to Pascal law, if the fluid is static, for a static fluid, P1 equal to P2 equal to P3, that will be equal to directly P. We can write. Right. So my dear friend, in a static fluid, what are all the forces will be acting in a static fluid? in a static fluid, what are all the forces will be acting? Static fluid. So there will be some pressure forces, Px. Let's suppose this is dy, this is dx, and width I am considering 1 unit. That is perpendicular to the laptop screen. The width I am considering as 1 unit. Width I am taking it as 1 unit, for example. So what is the volume of that element? The volume of that element will be dx dy into 1. So definitely there will be some body force will be acting. The body force will be acting like this. Rho, what is the body force? Body force, we know that mass into g. So rho into dv into z. So rho into dx into dy into z, right? So pressure force px into dy into 1, width will be 1, and here what will be the pressure value? Px plus dou p by dou x into dx into dy into 1. There will not be any shear force, right? There will not be any shear force. Getting my point? There will not be any shear force. Agree with me or not? If the flow is not happening, why the shear force will be do there, right? Now, but my dear friend, this is the condition about this static fluid. This is the condition about this static fluid. But if I will be talking about certain cases where the fluid element is subjected to some kind of torque, for example, right? That means the fluid is whatever the fluid element is there in a container, this fluid element is undergoing certain motion. For example, this fluid element is undergoing certain motion, a rigid body motion, for example. During that case also, any shear deformation will happen. See, that rigid body deformation means pure rotation. Pure rotation case means you will come to know in fluid kinematics when I will discuss about that. You will come to know there will not be no angular deformations, no angular or shear deformations. When there is a no angular deformations, my dear friend, then what the shear force will do there? That is also zero. Once again, if we just draw the fluid element, once again there will be pressure force into dy, px plus dou p by dou x into dx into dy into 1, that will be acting. Once again the shear, what we call the shear stress, that is going to be absent. So once again it is going to be absent, then what we can do? Once again the pressure will be same in all the directions, right? So this picture, whatever we have drawn for the static fluid, that is also applicable for body fluid element which is undergoing rigid body motions, right? Make a note of it. Fluids are incompressible, so there can be no deformations. No, incompressible fluid we can have, still we can have that shear deformations, when it is under motion. Getting my point? Whenever any fluid is there, when you apply little bit of shear force, it will start deforming continuously, right? See, in a fluid element, there are two types of deformations. Remember that. One is a volumetric deformations. Volumetric deformations are happening because of the what? Equal amount of shear stress, equal amount of normal stress which is being present there, right? Or we can say because of the normal stress, what is going to be happening? There will be some volumetric deformations will happen. Second, there will be some shear deformations, right? Whenever we do the derivation of the Navier-Stokes, what we used to tell, whatever the normal stresses are acting in a fluid element, we try to denote it, basically categorize into two components. One will be volumetric deformation, second will be shear deformations. That's why you have, do you know the Stokes hypothesis? Tell me, guys. Any one of you know about the Stokes hypothesis? Till now we discuss only first coefficient of viscosity, that is dynamic viscosity, right? We have not talked about what second coefficient of viscosity, that is lambda, right? That is basically denoting, this is denoting the shear deformation, this will denote volumetric deformations of the fluid element, right? So this basic concept and understanding must be there when you basically dealing with the derivation of the Navier-Stokes or basically what any other equations, right? So remember, any fluid element, you say, you take any fluid element, and whenever you just apply, let's say the this fluid element is under what motion, right? So what we used to do, we used to categorize into two things. One will be, we treat it like there is a hydrostatic state of stress where it is being subjected to equal amount of pressure value in all the directions. Second, we say it is undergoing volumetric deformations, it is also undergoing shear deformations, right? And likewise we used to determine the Navier-Stokes equations, right? But again, volumetric deformation will be zero for which case? Tell me, guys. Volumetric deformation will be zero for which case? That is a very, very obviously answer, right? Very, very obvious answer. All of you can answer that. Whenever the fluid is incompressible, there will not be any volumetric deformations. There can be only shear deformations, right? Volumetric deformation means what? dV by V, that is minus d rho by rho. Incompressible means this will be zero, this will also be zero. For a fixed mass, volume into density, when you differentiate that, this equation we are going to get. So totally we can say for an incompressible fluid, the volumetric deformation will be zero. Again, you might be thinking, sir, you are talking right now in the air, you are not writing anything. Sir, what the hell we are going to do that? How we can learn that? No need to worry. In fluid kinematics, once again I will discuss, and maybe if I will not do the derivation of Navier-Stokes, other aerodynamic faculty will do that. But you must understand what are all the steps involved there while doing the derivations. Not only we have to learn the derivation, we have to understand fundamentally also why these terms are coming, why that term is not coming. Because for a compressible fluid, whatever the Navier-Stokes equation you know right now, that may not be true, right? Because in that case, we have to again for a Stokes hypothesis, even for a compressible fluid, we say this this compressibility effect will not be considered, right? There are many situations, I will discuss that separately. Maybe if extra class will be permitted, I will take that derivation also, because that is a very, very important for being a fluid mechanics expert, that we should know about the Navier-Stokes fundamental things, right? Fluid rotation, we are saying the rigid body motion, because here, see, understand rotation is not only right now what you're understanding by rotations. Tell me, guys, what you are understanding by rotations. Rotation means whenever the fluid element you take, for example, when you take the fluid element like this, for a fluid element, suppose, and on a fluid element you are applying shear force like this, and when you take the radius, there will be some kind of torque onto this fluid element, that is force into radius. My dear friend, now this shear force is acting, and you know that whenever the fluid is flowing, for example, flow over the flat plate, there will be some boundary layer formation, there is some velocity gradient, as you can see over here, right? Now, even though fluid is having viscosity, even though it is having what, du by dy, right? So definitely there will be some shear force, mu into dou u by dou y into area. So definitely shear force is there, and radius of that fluid element will be there, so that will create the rotations. So one thing you are so sure about the rotation is that viscosity is responsible. What will happen? But that is a wrong statement, that viscosity is only responsible for the rotation of the fluid. The fluid can also have the rotation, still the shear force is zero, because see what we are writing, even though fluid is having viscosity, but dou u by dou y will be zero. Why it will zero? Pure body rotation. Suppose fluid element is there in a container, and I have just applied some torque like this with the help of this one. What will happen? Externally we are rotating, even though the region of the fluid element is not having shear force, that is zero, because Not the viscosity is zero. Viscosity is present, but dou u by dou y is zero. Pure rotation means there will not be any shear deformation. Only rotation will be there. Why and how, with the help of omega formula and all, I will discuss separately in the fluid kinematics. If I will discuss right now, you will say, sir, fluid statics, you are discussing fluid kinematics, you are mixing, you are confusing. So that's why I'm not giving you in detail. I'm telling you, even though I'm telling you that the viscosity is not the only parameter which is responsible for the fluid rotations. Even though you have the viscosity, but you don't have the shear force, then what will happen? Still, you have the rotationality effect in the fluid element because of what? External torque. Externally, you are providing some kind of rotations. Inherently, by the nature of the fluid, the particular fluid element is not able to rotate. He is saying that I'm not able to rotate by my own. So what you will say? No, I'm rotating you. You need not to rotate yourself. I'm rotating you. So that is what the rotationality effect will be coming into the picture. This is nothing but something like a what we say, pulley is there or any ball is there which is being hanging, for example, and we are just applying some kind of, or maybe we can just think of something like this. We are applying some kind of, to the disc, we are applying some kind of torque. So this is a solid body, this is a fluid element. That's why we say solid body rotation case. The pure whatever the pure rotation is there, or that's why the name itself is there. What is the name? Rigid body rotations, because disc, in engineering mechanics we are dealing with the rigid bodies, so that's why the name has been mixed there, that rigid body motions. Is that clear, all of you? We are not we are treating the whatever the fluid element just like a solid body, not exactly they are solid body, but we are treating like that. Is that clear, all of you? Because until unless we talk about the fluid element, we say there has to be some shear deformations. That's why the flow is happening. See that this is the fluid, this is a shear force we are applying, and we are saying there is a continuous deformations, and that's why we are saying there is a flow, right? So again, you might be thinking, sir, if we are talking about the fluid, we are talking about the motion, we are not talking about the flow, we are not talking about the shear force, then why the hell we are discussing in the fluid mechanics? We are applying some kind of external torque just like a solid body. That's why the name has been given solid body rotations. Solid, rigid. Getting my point? Is that clear, all of you? So yeah, make a note of it. So remember, for any fluid, there can be volumetric deformation, there can be shear deformation. For an incompressible fluid, straight away we disregard the effect of volumetric strain rate or volumetric deformations. Getting my point? See, the solid body, you are talking about the volumetric strain rate in a pure rotation. Once again, which kind of fluid? Whether it is a compressible fluid or incompressible. Incompressible, again, that is zero. Getting my point? Now, so please make a note of my each and every word, because at the time of fluid kinematics or fluid dynamics, little bit I will discuss, not in detail, because I am putting my here time. I am giving some time to this topic. That's why I'm gonna put some less amount of time during those basically topics. Now let's discuss some of the fundamental of fluid mechanics by Newton's second law. What are all the forces that is being encountered by the fluid element when it is being subjected to different types of forces? So I'm not deriving Navier-Stokes right now. I'm just giving you a little bit of hint so that you understand each and every terms in that equations. Because when you know Navier-Stokes equation, your life will become very easy. If you don't know, very complicated life will be. Any problem you will face very difficult to solve by without solving the Navier-Stokes equations, right? With the Navier-Stokes, automatically problem can be solved within 2 steps, or hardly any 3 steps will be taken. From this page only, there is a one statement, inviscid flow. What is the meaning of inviscid flow? Shear force is zero, viscosity is not equal to zero. Inviscid flow always be irrotational flow. There is a one statement they used to give in examination that do irrotational flow, do all inviscid flows, do inviscid flow always gives irrotational flow. Irrotational means omega will be zero. Omega will be zero. That means no rotation, right? Fluid element is not being rotating. That is the first statement, right? Second statement, you will encounter that do all irrotational flows gives inviscid flow. So for these two questions, we have a lot of motivation to study fluid kinematics, right? Because for every topic you are studying, you are investing your time, you are attending the classes, definitely some motivation is there, right, behind that. You are not coming just for seeking the formulas, seeing the particular, noting down the derivations, noting down this definition, because that is all there in the textbook. I'm telling you, you go and read that, but you may not be able to understand even single line also. But after my classes, definitely you will enjoy learning those paragraphs within fraction of second, or maybe hardly any time you will put from your end, you will be able to finish one complete chapter of that book, right? Now, so after noting down this thing, is it complete? All of you have noted down? So we have discussed the Pascal law, we have discussed the rigid body motions. Now, just note down the fundamental of fluid mechanics. Now, the fundamental of fluid mechanics, which I'm going to tell you, is that suppose there is a fluid element which is being subject to do different forces. This is a liquid molecules. No, every inviscid flow will not be irrotational flow. Inviscid flow can be rotational flow also, just like a solid body rotations, right? We have discussed that. Inviscid flow means shear force is zero, but still we externally we can provide some rotations, right? Inviscid flow means when shear force is zero, we say inviscid flow. When viscosity is zero, we say inviscid fluid. No viscosity. In means what? No viscosity. We also say ideal fluid. This we say ideal flow. Ideal flow may be possible, but ideal fluid will never gonna exist in real life. Now, let me draw the fluid element. If I just draw the fluid element from here, and if I zoom it, then I will be basically taking one cubical element, because that is a very easy shape in a Cartesian system. So those who are having confusion about the solid body rotations and whatever I have discussed, volumetric deformations, shear deformations, all those things will clarified automatically as we progress towards this syllabus, right? No need to get panic at all over here in the fluid statics or why we are discussing about those things. I would like to give some idea about that, and whenever we are discussing any topic, it is not necessarily that you should be stop thinking about some other topics or maybe other zone, that is fluid dynamics or fluid kinematics. Because after fluid statics, which picture will be started? Fluid kinematics only it will be started. Fluid dynamics only it will be started. No, because when I say about your aircraft which is flying at a particular altitude, you will never say how the motion is happening, right? You will always deal as an aerospace engineer what are all the forces will be acting. For that only you will be paid. You are not going to be paid, sir. How you are not going to be paid, how the diagram will be, whether it is a delta wing, whether it is a diamond wing, whether it is a some aerofoil shape, whether it is some normal subsonic airplane or maybe supersonic. You will not be there for that purpose. You as an engineer, you will be there what are all the forces you will be encounter. That is what we are discussing right now. Now, so any body fluid element will be subjected to different types of forces. Let's say this is a dimension dx, this is dy, this will be dz. This will be my x-axis, y-axis, this will be my z-axis. Any forces you will encounter here, net force, whenever you used to write mass into acceleration, acceleration can happen in x, y, z directions, right? Now, what are all the forces will be acting? The first one will be surface force. Second one will be body force. First force we'll be discussing here is that surface force. What are all the surfaces forces will be acting on a particular surface? Tell me, guys. One will be pressure force. Second one will be viscous force. And what are all the body forces? Of course, weight of the fluid element. Weight of the fluid element, right? Now, as far as the fluid is under basically what? In a motion conditions, we are dealing with this type of forces. One is a pressure force, second will be viscous force, and third will be body force. Now, what is the body force? So body force we are denoting by mg, that is equal to what? Rho into what is the volume of that element? What is the volume of this element? I am considering a small volume of dV in a whole liquid molecules. Volume of this element will be what? Dx, dy, dz, right? So volume of that fluid element will be dx, dy into dz, right? Into g, right? So my dear friend, what I can say, body force per unit volume. If I want to write, then what I can write? Dx, dy, dz. This will cancel out. So what will be my body force? Rho into g. Is that clear, all of you? Now, body force that can be acting in x direction, of course. As of now, whatever the figure you are looking right now, definitely the body force will be acting only in the y directions, right? There will not be any body force in x or z directions. But for the sake of generalized case, I'm just telling you the body force can be acted over here in x, y, and z direction. Let's say the fluid element is in an inclined plane, for example. In that case, this is the body force rho into g. But if you just draw the component, both the components will be acting, you know. So for a very generalized case, I'm talking about the body force that can be acted in the y, z, and x directions. Make a note of it. So all of you are understanding or not? Tell me, guys. Is that clear, all of you? The forces which is being subjected to, which is being subjected by the fluid element, because you will be having only pressure force and this air force, you know. That viscous force only in later part of the discussion in the fluid dynamics we say that drag force. Done. Can I move to the next segment? No. Okay. So here the fluid element which is being subjected to body forces, that is sorry, pressure forces, will be what in x direction. If I just write, that is p into dy into dz, because this is what dx dz, and this is what we have dy. So what is the area on which it is acting? Dy into dz. And what is the pressure force in this direction? P plus dou p by dou x into dx into dy into dz. Pressure into area, that will give me the force, right? And what are all these air stresses? What are all these air stresses, my dear friend? In a particular fluid element, what you have observed, suppose the plate is there which is being subjected to force F, and there is a fluid element. So generally what you have encountered, generally what you have seen, that when the force is acting like this, opposite direction there is a one force onto the fluid element, here like this, and here it is like this, shear force. Once again here it is shear force, here also shear force. So if you just take only fluid element, and if you draw the free body diagram, so what are all the forces will be acting? Shear force. How to write this shear force? So one will be this one, right? Second one will be this one, this one. What is that? Tau into area, tau into area, dA. What we can write? On which area it is acting? On this area it is acting. What is that area? Dx into dz. And on the top of that, when you just move towards a distance of dy, what are all the forces will be acting? Tau plus dou t by dou y into dy into area. What is that area? Dx into dz. Now, why the direction is different? It is being clear by the free body diagram, right? Now, so the net force in the direction of motion, that is equal to mass into accelerations. I'm writing x momentum equation. In the direction of motion, what is the motion? Let's suppose in these directions. So p into dy into dz minus p plus dou p by dou x into dx into dy into dz. That is equal to mass into acceleration. But mass, I have told you that what is the mass value we can write? And one more force is there, shear force, right? In the direction of motion, plus tau plus dou t by dou y into dy dx dz. Why plus? Because it is acting in the direction of motion, minus tau into, that can be written as, mass into accelerations. So mass can be written as rho into dv, acceleration in the x directions, right? So this will cancel out. So what is going to be left out? Minus dou p by dou x into dv plus dou by dou y of mu into, sorry, here we can write directly, I have written, we can write dou t by dou y into dv. That is equal to rho into dv into ax. Dv will cancel out. So what we can write? We can further write minus dou p by dou x plus. Now assume some body force also in x direction. Assume some body force also in x direction. What is the body force? Tell me guys, what is the body force? Rho into what we can write? Because we already only we have considered the pressure force and the shear force, not the body force. What is the body force we can write, my dear friend? The body force, for example, we can write bx into dy, bx into dv. So here we will be having bx also plus bx into dv. This will cancel out. So dou by dou y of tau plus bx, that is equal to rho into ax, where bx is what? Body force per unit volume. Body force per unit volume, correct. So what you are getting, my dear friend? And here we are discussing about the Newtonian fluids. So tau will be what? Mu into dou u by dou y. Directly we can write du by dy, or we can write dou u by dou y. So here you can write further this equation when you simplify, minus dou p by dou x plus dou u by dou y mu into dou u by dou y plus bx, that is equal to rho into acceleration. So you are, see, I'm not deriving any momentum equation or Navier-Stokes equation. I'm just telling you at least how you are getting terms and terminologies into that equations. At least you can feel that. For that purpose, I'm telling you, right? In a bigger picture, when you write the x momentum equation, right? When you do the complete derivations, you will be having this equation minus dou p by dou x plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus bx, that is equal to rho into acceleration, right? Y momentum equation when you write, minus dou p by dou y plus mu into dou square v by dou x square plus dou square v by dou y square dou square v by dou z square plus b y rho into ay. When you write the z momentum equation, minus dou p by dou z plus mu dou square omega by dou x square. See, what is the omega, v and u? U is a x component of velocity, v is y component of velocity, and omega is z component of velocity. Right? Plus bz, that is equal to rho into acceleration in the z directions. So you might be thinking, sir, you have done the derivation right now. Only we are getting this term, this term, this term, and this term. What about this term, sir? See, I'm telling you, when you do the full derivations, then only you will be getting the complete terms of Navier-Stokes equations. Right now, I have derived only few terms, so that at least you will be getting idea how those terms are coming. Right. My purpose is to tell you that this is nothing but pressure force. This is nothing but viscous force. This is nothing but body force. And the right hand side, this is nothing but actually telling you the acceleration, mass into acceleration or inertia force. Just make a note of it. It is just that we are discussing pressure, force and all per unit volume, per unit volume, per unit volume. Is it clear how the terms are coming? When you do the actual derivations, a big 5-page derivation is there. In that, you will be getting each and every term. But right now, for the sake of understanding little bit about the Navier-Stokes, I have taken about these cases. And now, what are all the assumptions? First is concept of continuum has to be valid. Second is we are assuming whatever the equation we have written, that is only valid for Newtonian fluids, because we have replaced this tau with this one, and that is only applicable for the Newtonian fluids, not for the non-Newtonian fluids. Now, all of you have noted down. Can I move to the next one? Done. So note on this equation very quickly. Now we will discuss each and every separate cases of inviscid flow, and for the you know for a hydrostatic when the fluid is at the rest conditions. Then also we will discuss this thing. Done. Is it over? See, dou p by dou y, what is the unit? Newton per meter square per meter. So Newton per meter cube. So that is a force, pressure force per unit volume. And remember, my dear friend, P is a scalar quantity. But what about dou p by dou x? Is scalar quantity or vector quantity? What is the dou p by dou x? Or dou p by dou y? Or dou p by dou z? Is scalar quantity or vector quantity? Because whenever you take the gradient of any scalar quantity, you will be getting the vector, right, from the mathematics. So definitely pressure is a scalar quantity that is not give you anything about the directions, but dou p by dou x, how the pressure is there, in a diverging section, when you see that there is a ed formations and flow suppressions from a certain particular edges of the diffuser, what you are observing actually, that is giving you the dou p by dou x as what? This will give you the dou p by dou x greater than 0, right? So that dou p by dou x is basically what? Greater than 0 means what? What is going to be happening? When this is going to be there, then what we can say? Adverse pressure gradient, correct? So actually dou p by dou x, with the help of that, you are able to identify the directions where the flow is happening. So that is a vector quantity. Now, for an inviscid flow, viscous force will be 0. Viscous force per unit volume, that is also going to be 0. So which term will be 0? X momentum equation minus dou p by dou x plus 0 plus bx rho into ax. Y momentum equation, my dear friend, what you will be writing? Minus dou p by dou y plus 0 plus by rho into ay. Z momentum equation, my dear friend, what you can write? Minus dou p by dou z plus 0 plus bz rho into az. This is nothing but Euler equation. Make a note of it. Suppose only gravity force is present, suppose gravity is present as a only body force, gravity only presents as body force, then what we can write? Bx will be 0, Bz will be 0, and what we can write? By, the body force in the y directions will be minus mg divided by volume, so that is equal to minus of rho g. Because see, actually standard coordinates is what? X, y, z, but gravity will be acting in the negative y directions. That's why minus rho g. According to our standard Cartesian system notations, No, 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 no. We have not started fluid kinematics. I have discussed only little bit about the discussion on the some rigid body rotations and those things. Is it done for all? Can I move to the next page? Done. Now, what here we are discussing when the fluid is under rest condition, when the fluid is at the rest, acceleration will be zero, either in y, z, or x. What about x momentum equation? Yeah, and fluid at the rest, so automatically shear force by default 0 per unit volume, or absolute shear force, that is also 0. So minus dou p by dou x will be 0. Y momentum equation will be minus dou p by dou y minus rho g, that is equal to 0. C, minus dou p by dou y plus by, that is we are writing as 0, but by is what? Minus rho g. Just now we have seen that, right? And what about jet momentum equation? That is 0, right? So from here what we can conclude, so pressure is not the function of x, pressure is not the function of z, that means pressure is only the function of y, right? So in a horizontal fluid system, right, there is a fluid suppose, and both are at the same level. So in the x direction at point number 1 and 2, the pressure will be same. If the fluid is continuous, then pressure will be same. That is the consequences of dou p by dou x equal to 0. And that is the basic principle of, that is only the basic fundamental thing we are applying in the manometer, right? The fluids which are continuous at the same horizontal level, directly we equate the pressure, right? So we are connected this to one limb, this connected to other limb. Suppose tank, we want to measure the pressure, we place it certain liquid called the manometer fluid, and whatever the height that is being raised will give me directly pressure value, because at this point we are just equating the pressure. Now, so what is the total value you are getting? Now, my dear friend, when the pressure is not the function of y and sorry, x and z, can we write dou p by dou y? That can be written as dp by dy. Tell me. The partial differentiation, we can write it as total differentiation, right? There is no harm in that, right? And if we can write like that, so I can just write this also, dp by dy minus of rho g. And that is what you are arrived to hydrostatic law. So what is the hydrostatic law? This law, it states that the rate of, yeah, the rate of increase of pressure in a vertical downward direction, in a vertical downward directions at a point in a static fluid of an incompressible fluid, or maybe compressible fluid. It need not to be compressible and incompressible. We will see that. That must be equal to a specific weight of the fluid. Because what is that? Specific weight. Weight per unit volume. That is rho g. Now, once it is done, let me know this particular slide. So, even though basic understanding we can derive from the Navier-Stokes equations, right? Please note down Navier-Stokes equation. These are the Navier-Stokes equation. Don't think that Navier-Stokes is of something like a rocket science of things, and we are only discussing in the fluid dynamics. See, we have arrived to the conclusion of fluid statics law with the help of Navier-Stokes. So when you play with the Navier-Stokes equation, you do not to worry so much about the fluid mechanics, or maybe I would say up to some extent aerodynamics. Done. All of you have noted down. Note down, guys. Yes, correct. So note down hydrostatic law. Pressure in a liquid at the rest increases linearly with the distance from the free surface. That we will arrive to the conclusion of this one. But before that, you note down hydrostatic law. Hydrostatic law. This law, it states that the rate of increase of pressure, the rate of increase of pressure in a vertical downward directions at a point in a static fluid must be equal to local specific weight of the fluid. That means dp by dh must be directly proportional to rho g. So when you know the RTT equation, Reynolds transpose theorem, even most complicated problem you can solve by that equation. But why students face difficulty in solving the problem by RTT? The complexity involved in that equations. Whether we have to consider a reference frame that is stationary or that is moving, right? That is actually the difficulties in that. And one more assumption is there in that Navier-Stokes or ITT derivations. What is that? Regarding frame of references, tell me, guys. That should be inertial frame of reference, right? That should not be non-inertial frame of reference. That should be inertial frame of references. That means you are as an observer. uh, yeah, you are as an observer. Yeah, they will be directly proportional, or they will be directly what we can say. Yeah, sorry, here I have written. Yeah, you can write dp by dj something like this. Now regarding sign, whether it is a minus rho g or plus rho g, that is will be clear when we discuss about further. you know Further, if you simplify dou p by dou y, or dp by dy, this we have written is equal to minus of rho g. That is according to sign convention, this one. Plus you can write, when you write the y direction like this, you are taking downward direction of y as positive, then you will be getting the equation dou p by dou h or dp by dh as rho g. Anyway, any sign convention you follow, you will be getting pressure equal to rho gh. Let me prove that. Now once it is done, let me know. See guys, understand. Here when you try to observe, what is the equation we have? dp by dy minus of rho g. Yes, this is my y direction, this is my x direction, or maybe I can write over here at the bottom one. I can write here something like this, and this is my point number one, and this is my point number two, for example. So can I write dp equal to minus rho g into dy, and can I do the integration from 1 to 2? What should be my limit? Suppose this I'm taking as a reference, that is a zero value of y, right? And I'm moving in the downward directions. I'm moving in the downward direction towards the point 2. Actually, I'm moving towards the downward. And my sign conventions is that if I move upward, then I will take positive h. But if I move downward, I will take minus h, right? So what we can write, p2 minus p1, that can be written as minus rho g integration dy 0 to minus h. Remember, when only you can take the rho outside the integration, when it is incompressible fluid. Or we can just take when the density is not varying with respect to height, right? So what we can write, minus rho g minus h, you will be getting p2 minus p1 rho g h. For example, if p1 is p atm, then p2 can be written as what? P atm plus rho gh. And that is how you can see that pressure will vary linearly with respect to height, right, from the free surface. Make a note of it. Perfect, correct, absolutely correct. But generally we apply RTT for converting the control, whatever the system approach to control volume approach, because whatever the Newton's law is applicable, that is for the solid body, for a single particles. And if you want to convert those law for the fluid elements, because see, whatever the Navier-Stokes equation we have derived, why we have written by using this one. And what is the condition for that? Newton's second law, that definitely has to be applied to some particles, single particles. But we are able to apply for a control volume just because we should be thankful to RTT. That converts the actually the necessity of basically what, system to control volume, right? Getting my point? Even you can derive the Navier-Stokes from a RTT equation also. That is what I told you, the conditions, right? That should not be inertial, that should be inertial frame of reference. Getting my point? What is the meaning of inertial frame of reference? That means acceleration should be zero, right? Is it done? Shall we see the actually the how it is varying linearly? Let's focus on that. As you can see, by different the pressure is varying from here. Actually, this should be have the variations, something like this. At this point 2, at this point 1, pressure should be at this point should be rho gh for a height h. But if I take pressure 1 equal to 0, what we can write directly? P2 will give me the values of P gauge, right? And that is what we have. They are varying linearly. Make a note of it. See, these are the very, very small thing, guys. Maybe directly somebody will be there who will be telling you pressure equal to rho gh. You please note down directly without any derivations. But you only have seen with your own eyes that how difficulties is there, even to arrive a very simple conclusions. We should know fundamentally each and everything, so that any difficulty in a examinations, in a particularly examination. Hello, I'm audible. I'm audible. Yes. In examination, suppose examiner has given you something like this. You should not get panic. They will mention the coordinate system also. Getting my point? If they will not mention, we have to assume our standard sign conventions, or in a paper they will directly mention. So whenever you see minus rho g is not there, sir, then how we can proceed? No need to panic, because with this also you will be getting the same thing. How? Let's see. For this one, what is the sign conventions? This is my sign convention. That means if I move in the negative y directions, I will be writing plus h, right? I am considering this as positive y, this as negative y. So point 2, point number 1, 0 to h. So I will be getting what? P1 minus P2, or sorry, 1 to 2, right? Here I need to write 1 to 2. So P2 minus P1, once again you will be getting what? Rho gh. It's only the matter of sign convention for a coordinate system. Getting my point, all of you? So actually, I'm telling you all the conclusions of different textbook. When you follow any other textbook, they try to mention like this. Sometimes they used to follow different sign conventions, but our standard sign convention, which we follow from our childhood days, that this is y, positive y, this is positive x, this is positive z. And what is the standard for the rotation angle? Anti-clockwise, that is positive. Clockwise, that is negative. That is our standard one. I'm not saying that in examination anti-clockwise always will be positive. They will mention, they can mention negative, but I'm telling you what you actually guys have followed from basically what your 10th standard or 11th standard. That is what we are considering over here. Now, is it done for all of you have drawn this one? Can I move to the next segment? But do we have only linear variation of pressure with the height? We don't have any other variations like exponential or any other variations. Tell me, guys. Do we have only the linear variations? As you can see, there is a linear variations. Don't we have any other variations? Yes, we have the variations. Let's focus on that. Now, note down. Important note. Ideal gas in isothermal conditions. Ideal gas in isothermal conditions. Now, guys, try understanding. So, for example, you have the suppose Earth surface. As you march if you just going higher the altitude in isothermal layer, you might be having the variation of pressure, definitely variation in the density, but we are assuming temperature to be constant, for example, right? So my dear friend, what we can write at the earth surface, we have the condition like p naught at, let's suppose y equal to 0, we are moving like this, and we are very much interested to calculate what is going to be happening about the pressure, about the density at y equal to small h. So for that, definitely we have to apply the hydrostatic law, that is dp by dy minus of rho g. So now dp can be written as minus rho g from integration if we do, but here you cannot take density g as constant. Density rho directly you cannot take outside of the integrations, because right now from ideal gas law, p is equal to what? Rho RT. Being temperature constant, so rho will be what? Something constant divided by p. Sorry, so p will be what? Directly proportional to rho. So further, what we can write rho? Rho can be written as p divided by what? RT. Getting my point? So if you just write this one into that equations, and integration we are doing from p naught to p, and y is varying from 0 to positive h. Why positive h? Because we are moving like this. According to standard sign conventions, that is a positive value, right? So when you write p minus, sorry, here we have to perform dp by p, p naught to p, minus g by rt, that is constant, dy 0 to h. So when you just write log of p, that is from p naught to p, or maybe you can write p dash rho dash, p dash p dash. Now here you can write minus g divided by rt into h. So ln of p dash divided by p naught, that is equal to minus gh divided by rt. So p dash can be written as p naught into exponential of gh divided by rt. So how the pressure is varying with the height? Exponentially. So when you just write the variations, this is varying as exponentially. This is actually varying the not linear manner, it is varying exponentially. Is that clear for all of you? Tell me, guys. Is that clear? Yes. One question also.
Explain again.
If it is done, let me know.
Yes, sir.
Done? Is it done? Now, when you see this particular question, consider the density and altitude at the base of an isothermal layer as rho 1 h1. The density variation in the layer is governed by which law, right? So what will be the answer for this question? That's a pretty straightforward. because we have seen the pressure variations, and pressure will be directly proportional to density. So similar way, the density will also vary. Please try that. No, check it out once again. Very carefully, you please observe that. So instead of basically, we have just now seen that p dash by p naught, that is equal to exponential of, or e to the power of minus gy by rt. This is what we have seen that. But here they are mentioning that particularly layer height from h1 to something h, they are asking. Somewhere the reference is 0, right? We have taken the reference from 0. So if you just do the integration, minus dp by p from what you can write, that is what we can write, p1 to p, that is equal to minus g by rt into dy from what we can write, h1 to h. So ln of p divided by p1 minus g by rt, h minus of h1, z naught they have mentioned in the problem. So let me take z naught only. So further, what we can write, my dear friend, p by p1 minus z naught by, sorry, exponential of z naught divided by rt. This is the pressure variations, and we know that pressure is directly proportional to density. So that will be rho by rho 1 exponential of, because p you can write rho rt, and this you can write rho 1 into rt. This will cancel out. In isothermal layer they have mentioned. So we can have minus g naught divided by rt, h minus of h1. So if you don't do the derivation, definitely you will be having challenging in solving this, even though simple problem. Whether I should be taken from h1 to h, or h to h1, or h1 to minus h, something like this. That's why if whenever we learn any formula by the derivation, definitely it is having some advantage. And you need to be a little bit patient also, because nobody have that much of patience in understanding the derivations, then formula, then solving the numericals. They directly jump to second step, that is learning the formulas, apply to the question, get the answer, that's it. Especially when you are sitting at the examination hall, chances of committing the mistake is very high. If you're sitting at the room solving that, there is no big deal in that. The whole problem will be arising when you just go basically going for the deciding day, that is actual day of the gate exam. How well you are able to perform during those 3 hours movie, that is only the matter of concern. That is only matters, actually nothing matters. Before that day, what you are doing for the past 8 months or 9 months, that will be reflected directly in the results. So that is, they used to say compound interest as the seventh wonder of the, maybe eighth wonders. When you just do any investment, and when you do the compound interest of that, definitely the return on investment will be very high. But believe me, I don't think that that should be the correct one. Of course, that is correct mathematically. When you do the compounding, definitely our rate, whatever the return on investment will be very, very high. But actual investment is this gate exam. when you can play with these 3 R's, the return is quite high. You cannot believe also. Now, is it done, all of you? Can I move to the next topic? Now, hydrostatic paradox, let's discuss about that little bit. Now, note down the next topic. Hydrostatic paradox. All of you can see this one. Note down the topic name, hydrostatic paradox. Anyone know this one? The pressure in a fluid which are at the rest condition, which is not moving in a container, it is at the rest condition, is independent of the shape of the container or the cross section of the container. It only changes with the vertical distance but remains constant in other directions. You know, dou p by dou x equal to 0, right? Yes or no, guys? It only varies in the y directions. It will not vary in the x direction or in the z directions. That means if you just see here, PA, PB, PC, all are having the same pressure value because height of the liquid is being same. H only. Even the shape of the container, the first one is a rectangular one, second one is quite different than the rectangular one. Third one, C point is on the circular track. Again, D is there on a particularly what? Some other track. Then E point you have. But here the precaution is the height should be same. And the water molecules or whatever the liquid molecules is there or whatever the liquid is there, that should be same, right? Because pressure value is not only depending on the height, it also depends on rho. The moment you are changing the density, even though same height is there from here to here, capital H, but still pressure at H is equal to what? Not equal to pressure at I. Why? Because pressure value at H point will be rho of water G of height plus rho of mercury G of H minus small h. But when you just look at the pressure at I point, what you are observing? Rho of water G into capital H. As you can see, they are not equal. Irrespective of the shape of the container, why they are unequal right now? Because of the liquid changes. So pressure value at a particularly horizontal level, all the horizontal level will be same. That is equal to rho gh. Is it done for all? Which one? Which particular portion I should be repeating? See, hydrostatic paradox, it is saying that when you have the liquid that is not moving, when you place in any shape of the container of the same height, same liquid, the pressure value at the bottom of the container will be same. Whether container shape is rectangular one, circular container, spherical container, or triangular container, whatever it may be, the pressure value at the bottom of that container will remain same until unless you are changing the liquids. That means pressure value at H point, as you can see, the total height is remain same for H point and I point, but still the pressure value is not same, even though shape of the container is different. Why? Because here you have the water up to some height, then you have the mercury, but here when you see only water is there. right? But apart from these 2 points, when you consider A point, B point, C point, D point, E point, F point, G point, you have the pressure value exactly equal to P ATM plus rho GH. Yes or no, guys? Can I move to the next one? So you might have heard about the hydraulic jack or hydraulic lift, right? So that is also working on the principle of what? No, PG will not be equal to PI. Why? The height of the liquid is different. Getting my point? As they are having different heights, what is the PG value? Rho of water G into small h. And what is the PI? Rho of water into G into capital H. All of you have noted down? Can I move to the next one? Done? So note down the next particular concept, that is hydraulic lift. Okay. Note on this one. So with a small effort, how can the particular in automobile industries, you have seen that they are lifting the car for some maintenance purpose or some doing checking and all. They used to lift this one by the hydraulic jack or hydraulic lift. That is basically working on the principle of what? Same thing. Dou P by dou X that is equal to 0. That is a Pascal law. We also say hydraulic lift. So what you are observing, pressure at one point for this particular fluid which is being traveling, you know, that is being continuously present, then what we can write, pressure at 1 that is equal to pressure at 2, right? Because both the points are at the same level. Dou P by dou X equal to 0, right? There is a no variation of pressure in the X directions. So what we can write, P1 is what? F1 force, we are applying little bit of force and we are lifting a very huge weight, that is equal to what? The weight of the what we are calling the car. So as you can see here, F1 will be what? F2 A1 by A2. A1 is what? Less than A2. So definitely F1 will be less than F2. So with the little effort, right? And F2 is what? The weight of the car. Dou P by dou X means what you can write? You can write there are 2 points, 1, 2, and the distance is, for example, it is at a distance of x1 and x2. So what we can write? P2 minus P1, and whatever the gap is there, that is equal to 0. So P2 will be equal to P1. Points which are on the same level in the x direction will have equal pressure, and that is the basic principle behind the manometer, which is used to measure the whatever the gauge pressure of a container. Is it done? Now let us discuss some of the basic fundamental, at least some definitions of hydrostatics or fluid statics, and then we can start with the pressure measurement devices, that is barometer, piezometer, manometer. Is it done for all? Is it done? Now note on the few concept, that is introduction to fluid statics. Fluid statics deals with the problem associated with the fluid at the rest conditions. Fluid can be either gases or the liquid. Fluid statics generally referred as hydrostatics when the fluid is liquid, but it is referred as aerostatics when the fluid is a gas. When the fluid is under rest condition, there will not be any relative motions. When there is no relative motion, there will not be any tangential stresses, right, in the fluid element which is trying to deform it. The only stress we deal in the fluid statics is normal stress, which is nothing but pressure. And the variation of pressure will be happening only with the due to what? Weight of the fluid element. As you they are talking about this case, weight of the fluid element. Only variation will be there because of that. When the fluid is moving with some constant velocity, still we can apply this law. This dp by dy equal to minus rho g. Getting my point? When the fluid is moving with some constant velocity, still we can apply this law. Again, I'm asking. Think carefully. Again, you just think and tell me. When the fluid is start moving and it is doing motion under constant velocity with no accelerations, whether we can apply dou p by dou y equal to minus of rho g. Tell me guys. Why you can apply? How you can apply? Tell me. When the fluid is start moving with a constant velocity, definitely say force will be coming into the picture. Then definitely this will also be coming. Dou square v by dou x square plus dou square v by dou y square. This term will be coming. Then how can you apply? Getting my point? Yes or no? The viscous force will be zero when under two case, when it is rest or when it is under doing the rigid body motion. But again, in the rigid body motion, the body will have the acceleration. So once again, this law will not be applicable. Getting my point or not? Tell me guys. Is that clear? Because in MSQ, they can ask even with the very basic fundamental things. If that is clear, you can just throw that question like anything in examination hall. And remember, when you are able to solve those type of problem, then only you can expect some good rank. Otherwise, don't think that, sir, with the less understanding, I will be focusing on some subjects. I will be getting 60 marks. As I know that 60 marks, rank 1 will be there. Don't fool yourself like that. Many aspirants are there who is just doing the hard work and understanding all the subjects. They are attempting some good number of questions, good mark. From that, they are getting low marks. And if you are attempting only that many marks, believe me, you will not be able to get more than 40 marks. Right? So don't be so smart in preparation that I'll be studying only those few topics based on the previous segments, based on the previous year content, and I'll be getting the good rank. Right? That is some in hypothetical or maybe in imagination world you are right now. If you are thinking like that. Now, is it done? We will discuss one, maybe what we can do. We shall close it because I want to start freshly about the barometer, right? Because the moment you talk about the fluid motion, shear force will be coming into the picture until unless it is a rigid body motions. This will be zero for rest or for a rigid body motion. So always remember you should aim, basically aim for a higher marks. I will be attending basically what 85 plus marks. In that you may be getting 60 marks or maybe 65 marks or maybe 55 marks depending on the level of the question paper, right? Always aim for attempting the very good number of questions for a very good marks, very high marks. In that definitely you'll be getting some 20 marks less than that. That is a general statement for all the, especially what I have observed in the aerospace, because I have talked about basically I have basically what I have the conversation to the basically what with the toppers. They have said that this thing they have attempted somewhat 80 plus marks. In that they got something like 60 marks, or some of the students they got like 55 marks. And this year I think 55 marks, 25 rank was there, right? Yes or no, guys? For 2023. Correct. Because one of the students I know that uh, he was continuously in touch with me, as he was asking the test series, mock test series question and all. So he was only telling me that I attempted some good number of questions, but that got incorrected. So he landed up getting this 55 marks exactly. So do not neglect any simple topic also. We are dealing with a very low topic. I'm telling you, this fluid statics is zero. You may not be able to get single question also, but if you are getting question, you make sure you attempt correctly that particular question. Don't do any kind of mistakes. And you can see that I'm not dealing with only fluid statics. I continuously basically invoking the or maybe indulging some other topics of fluid dynamics and fluid kinematics, right? So that we can link the topics or we can connect the dots between the topics of a particular subjects, right? Okay, guys, thank you. We can see on Tuesday remaining topics, or maybe Wednesday, right? So only we left with the two topics, hydrostatic forces, and then we are left with the topic of this pressure measurement and hydrostatic forces. Then we will start the fluid kinematics. Surface tension. You are from mechanical, Sanjeev? No, that is not that important. I will be discussing in separately for the mechanical. If you want it, you can attend that session. Capillary action, surface tension, I will be dealing separately for mechanical, because that is not that important. Because surface tension, that is also one type of force which will exist when the fluid is at the rest conditions. But we have the very negligible value of that surface tension. Okay, guys, thank you.